a new drug candidate to a primate. The dose is 2 milligrams per kilogram and is administered as a suspension in 20 ml of cherry syrup. They give you the following plasma concentration data to analyze. Fit the best model to the data, discuss how you select the model and the rate and extent of absorption, distribution, and elimination of the drug in this primate. So what you do, you copy, okay? You have a single dose, and then we go to Phoenix. We want to do a new worksheet. We're going to add time, and the unit of time are hours. And then we add the concentration, and the unit are, let's see, the unit are microgram per liter. Okay. And then I'm going to paste. So again, I'm going to send to plot. First thing, always plot the data. This is it. I'm going to see on the semi-log paper. Okay. So what does it look like? It looks like it's an oral administration. So I would say the third choice will be to try linear kinetics with two compartment models. What do you think? You have after the peak, this is an oral administration, you see two phases. So I would go back to the worksheet. I'm gonna send to the classic modeling, and then of course I have time and concentration. I'm gonna choose model 2 compartments. So I'm gonna go first order absorption, macro constant, no lag time. It looked like it was. So this will be the model, all right? And then I'm gonna do the dosing. The dosing, the time was 0, and the dose was 2 milligrams per kilogram, was 23 kilograms, so it's gonna be 46 milligrams, all right? The dose is 46, the unit is milligram. I put the 1 over y, is always y, so right, to put the weight. The initial estimate, don't have to worry, the units is correct. The stripping dose is equal to the dose, so it's 46 milligrams, all right? So everything is done, I run. Oops, 3% a little bit whoa. The 3% look pretty big. Let's look at the graph. Look at that. Oops. What happened? You see, it's well, on the semi-log doesn't even look that bad, all right? But so look at the residuals. A kind of, you know. So in this case, I would say what is more alarming is this high CB percentage. So you see, before the CB percentage was normal and the graph looked bad. Here, the graph after all, it doesn't look all that bad, I would say, you know, even though you can see that first of all, is also, you know, you have a 2-compartment model, but the predicted, it doesn't look 2-compartment at all. Can you see it? You know, after the peak, you you don't have two phases. But of course, if we do one compartment, so this would be, look like maybe, well, that Y could be a reason, all right? Let's go back to the final parameter. That may be the reason, maybe it's because it's one compartment, but so we can go back to the worksheet, all right? Or let's go back here, and then send it, set up. Model selection, we try a first order with one compartment. The doses, everything there, all right, so let's do it. But the CV percentage is still high. Let's look at the fitting. Well, the fitting is not really that much better. Again, it's not really good. So at this point, we can also see something that it looked like at the beginning of the curve is okay. What we have a problem is after the peak. The fitting, the bad fitting is after the peak. So one possibility is to go and to do the non-compartmental, okay? The other possibility is, because the question, your boss want to know, you want to enter, the extent of absorption, distribution, elimination of the drug in this primate. So we're going to try to do what we did today. We're going to see if it's by chance a nonlinear. So we're going to go to the classic modeling again. We choose the Michaelis method. And then we select, not the bolus this time, we're going to select the first order with no lag time. And we're going to have 3 constants also here. The initial estimate, oops. Now the parameter are V over F, K01, Vm, and Km. Now, V over F, I have it before. Let's see. Maybe V could be the same, at least could be something we have from before, all right? So let's do this. Let's look at the parameter. We don't have it. Yeah. Let's look here. The volume distribution I give 220, why not? So we can put 220. And K01 is 0.4, all right? So we're going to use this, all right? So we're going to do the initial, what we said is 220?
220.
K0 with 0.4. And Km and Vm, I can put 500 and 500 again. I can put the weight, again, 1 over y. The model selection, I already said. The constant now. The constant will be 1 administration. What should I put in the dose now? They were 46 milligrams. But, sorry, the concentration is in micrograms, all right? So I need, this is the Michaelis method. I'm going to put so I'm going to, what I put here?
46,000.
46,000. Yes, okay. And the time is 0, okay? Let's see. Oops, there are narrow wires executing, so what I did. Maybe I put time and concentration. verification, it has a... Maybe I did in my office. So let's take out, maybe we do 100 and 100. Let's see, probably it's a problem, but this one for the oral administration is more difficult to find the initial guesses. So you can just keep doing it, you know, and you know that. So, and you get it, all right? So these one are good data. Again, this is not going to be that easy, you know. So, but you see now that you have a good fitting. So this is telling us that this drug has a nonlinear elimination because the model, the compartmental modeling was not fitting. You know, we had a high CV percentage, we had a poor fitting mostly after the peak. So instead, when we applied the Michaelis-Menten, we came almost a perfect fitting, right? So we're gonna see, let's look at also the CV percentage. The final, look at that, the small, the estimate, we have, you know, so these are why, you know, the volume of distribution look a little bit big, but again, remember that this is V over F, all right? So V over F means that is the real volume of distribution divided by the fraction absorbed. So the fraction absorbed is 0.1, all right, means you multiply your volume of distribution by 10. Any question? Does it make sense? So what you want to write here, you're going to, at this exam, also in the exam or in your homework, you tell me the story, all right? You plot the data, you try the E-simple model, and then this was not working. You tell me why you think it's not appropriate, and then you test another model, all right? So in the exam, you know, it could be something like this that you have to decide between linear and nonlinear decay, or could be something like we did in the past. We didn't really do a formal homework with the report, but again, you have to choose between, let's say, 2 compartments and 3 compartments, all right, or something like this. So any question? Is it, do you like this, or is it's again the fact that, you know, it's not all that they might